In 2013, a geochemist standing deep within the bowels of a mine in the Canadian Shield did something that would terrify most people. She lifted a vial of water collected from a fracture in the rock face, brought it to her lips, and tasted it. This was not the fresh, cool water of a mountain spring. It was viscous, almost like a syrup. It was overwhelmingly salty, carrying a concentration of salt 8 times higher than the ocean. It had a bitter, metallic tang that lingered on the tongue. But the most terrifying and wonderful thing about that mouthful of water was not its taste, but its age. That fluid had been trapped inside the rock for over 1.5 billion years. It had been isolated from the surface of our planet since before the time of multicellular life. This moment at the Kidd Creek Mine in Ontario was not just a curiosity. It was a watershed moment in the history of geology. It shattered the long-held assumption that groundwater is something that only exists in the upper few hundred meters of the Earth's crust. It revealed that beneath our feet, kilometers down, there is a hidden hydrosphere, a deep crustal hydrology that is not a static tomb of rock, but a dynamic, living system. Today, we are going to explore this dark ocean locked in stone, understand the chemical engines that power it, and see how it reshapes our search for life in the universe. To truly understand the Earth, and potentially the habitability of other worlds, we must look beyond the blue oceans on the surface and peer into the black, saline oceans locked within the stone. For decades, the science of hydrogeology was effectively a science of the surface. We studied aquifers, water tables, and the hydrologic cycle that we all learn in school, where the sun evaporates water, it rains down and flows into rivers. In this traditional view, the deep crust, that crystalline basement rock that forms the continental plates, was considered dry and impermeable. It was just the solid foundation that the wet world sat upon. We now know this is categorically false. The continental crust is not a solid block. It is riddled with fractures, microscopic pores, and ancient fissures. While these individual spaces are tiny, often invisible to the naked eye, when you add them up over the volume of the entire planet, the numbers become staggering. Recent estimates suggest that the groundwater stored in just the top 10 kilometers of the Earth's crust amounts to approximately 44 million cubic kilometers. To put that number in perspective, that is more water than is held in all of the Earth's ice sheets and glaciers combined. This is a volume of water that rivals the shallow seas of the ancient Earth. But this water does not behave like the water we know. It does not flow like a river or crash like a wave. In the deepest sections of the crust, this water moves at a glacial pace, sometimes migrating only a few meters over the course of millions of years. Scientists often refer to it as fossil water, a term that implies it is stagnant or dead. However, a more accurate descriptor is an ancient fluid system. These fluids are highly evolved brines. Over eons, they have interacted with the surrounding rock, dissolving minerals, concentrating salts, and changing their chemical composition until they become something entirely different from the rainwater that originally fell from the sky billions of years ago. The premier laboratory for understanding this deep world is the Kidd Creek Mine, a massive copper and zinc mine north of Timmins, Ontario. It is here that we find the clearest evidence of deep time. As miners chased veins of ore deeper and deeper into the earth, eventually reaching depths of nearly 3 kilometers or 9,800 feet, they began to encounter fractures that were gushing with water. This was unexpected. At that depth, the pressure is immense and the rock should be tight. But the water was there. To determine how long that water had been down there, scientists analyzed the noble gases dissolved in it. They looked specifically at isotopes of helium, neon, argon, and xenon. Noble gases are the perfect timekeepers because they are chemically inert. They do not react with other elements. They simply sit there and accumulate. For example, helium-4, accumulates in the water from the radioactive decay of uranium and thorium naturally present in the surrounding rock. It is like an hourglass. The more sand in the bottom, or the more helium-4 in the water, the longer the bottle has been closed. Neon-21 is produced when alpha particles collide with oxygen or magnesium. By measuring these delicate ratios, the researchers found something shocking. The residence time of the fluids found at 2.4 kilometers depth was roughly 1.5 billion years. When they went deeper, to 3 kilometers, the water dated back 2 billion years. To understand the scale of this water was sealed in the rock around the time of the Great Oxidation Event, when oxygen was first beginning to accumulate in our atmosphere. This water is a time capsule, preserving a sample of the Earth's early atmosphere and ocean chemistry from a time when the planet was a radically different place. But the question remains, how does water sit in the dark for 1 billion years without becoming a dead, sterile chemical wasteland? The answer lies in the rock itself. The deep crust acts as a massive chemical reactor. Even without sunlight, there is energy down there. The primary driver is a process called radiolysis. The deep crust is rich in radioactive elements like uranium, thorium, and potassium. As these elements decay, they emit ionizing radiation in the form of alpha, beta, and gamma particles. When this radiation strikes a water molecule, it splits it apart. This is known as the radiolytic splitting. The water molecule breaks down into hydrogen gas and various oxidants, like hydrogen peroxide and sulfate. This is a profound realization. It means that the Earth is continuously producing hydrogen gas, a potent fuel, completely independently of photosynthesis or any surface biological process. It is a slow-burning, nuclear energy source. Alongside radiolysis, there is a second process called serpentinization. This occurs in rocks that are rich in iron and magnesium, known as ultramafic rocks. When water reacts with minerals like olivine in these rocks, the crystal structure changes. The rock literally hydrates, turning into serpentine minerals. This reaction is highly exothermic, meaning it releases heat, and it produces highly alkaline fluids and, crucially, massive amounts of hydrogen gas. But the chemistry gets even more interesting. The hydrogen produced by these rocks can react with inorganic carbon, like carbon dioxide, to form methane and water. This is known as the Sabatier reaction, or abiotic methane synthesis. It is the creation of a hydrocarbon fuel without any biological life involved. So in the deep, dark crust, we have a chemical soup that is rich in hydrogen, methane, and sulfate. In other words, the deep crust provides a buffet for any organism tough enough to live there. And this brings us to the most profound implication of deep crustal hydrology. Where there is water and chemical energy, there is life. We are not talking about surface bacteria that accidentally washed down a crack a few years ago. We are talking about an ancient, deep biosphere that has evolved in isolation for millions of years. In the deep gold mines of South Africa, such as the Mponeng and Beatrix mines, scientists have found life thriving at depths of 3 to 4 kilometers. The star of this deep show is a bacterium with the incredible name of Desulforudus audaxviator, which loosely translates to the bold traveler. This organism was discovered in fluid 2.8 kilometers deep in the Mponeng mine. What makes the bold traveler so unique is that it is a one-species ecosystem. On the surface, life relies on a food web. Grass eats the sun, the cow eats the grass, the wolf eats the cow, and bacteria eat the wolf when it dies. But down there, Desulforudus is all alone. It has everything it needs within its own genetic code. It fixes its own carbon, it fixes its own nitrogen, and it fuels its metabolism using the hydrogen and sulfate produced by the radioactive decay of the rocks around it. It is a chemosynthetic organism living on nuclear energy rather than solar energy. It is an alien on its own planet, and it is not just bacteria. In the Beatrix gold mine, researchers found tiny worms, nematodes, living in stalactites formed by fissure water 1.4 kilometers underground. These organisms were grazing on bacterial biofilms. This proves that complex, multicellular life can exist much deeper than we previously imagined. It challenges the very limits of where we think life can survive. But the story of Earth's deep water goes even deeper than the crust. It extends into the mantle itself. In 2014, scientists were analyzing a diamond from Brazil. This was not a gem-quality diamond. It was a trash diamond, brown and scarred. But inside it, they found an inclusion of a mineral called ringwoodite. Ringwoodite is a mineral that only forms under the extreme pressures found in the transition zone of the Earth's mantle, located between 410 and 660 kilometers deep. This diamond had been blasted up to the surface by a volcanic eruption, carrying the ringwoodite with it. Crucially, the crystal lattice of this ringwoodite contained hydroxide ions. It was about 1.5% water by weight. That sounds dry, but if you apply that percentage to the massive volume of the Earth's transition zone, it implies that this layer of the Earth holds 3 times the volume of all the surface oceans combined. This is not liquid water sloshing around. It is water bound within the molecular structure of the rock, but it is water nonetheless. This proves that the Earth acts as a massive sponge. It cycles volatiles from the surface, dragging wet oceanic plates down through subduction zones into the deep interior, and then releasing that water back out via volcanism. This deep water cycle is likely what has kept our surface oceans stable for billions of years. Without this cycle, Earth might have lost its water to space and become a dry desert like Mars. Speaking of Mars, the study of deep crustal hydrology has completely rewritten the rulebook for astrobiology. We used to think a planet needed to be in the Goldilocks zone, the perfect distance from a star where liquid water can exist on the surface, to be habitable. But if life on Earth can survive for billions of years in deep, dark, isolated fractures powered only by water-rock interactions, then surface conditions might not matter as much as we thought. Consider Mars. The Martian surface is a horror show of radiation, freezing temperatures, and dryness. But the Martian crust is ancient and basaltic, very similar to the Earth's deep crust. It is highly probable that deep liquid aquifers exist beneath the Martian cryosphere, kept warm by the internal heat of the planet. If life ever evolved on Mars during its wet past, it likely retreated into these deep, warm, radiolytic sanctuaries billions of years ago. The methane plumes that we occasionally detect on Mars could be signatures of this deep, abiotic serpentinization. Or perhaps, they are the breath of a deep biosphere. The same logic applies to the icy moons of the outer solar system. Enceladus, a moon of Saturn, and Europa, a moon of Jupiter, have subsurface oceans sitting atop rocky cores. The chemistry driving Earth's deep biosphere, specifically serpentinization releasing hydrogen, is almost certainly happening on the seafloors of these moons. The hydrogen plumes detected erupting from Enceladus are direct evidence of this hydrothermal activity. We look to the stars to find the alien and the unknown, yet we are standing atop a world just as foreign. Deep crustal hydrology has revealed that the ground beneath us is not solid, dead rock. It is a vast, fluid-filled lung that breathes on geological timescales. It stores oceans of ancient water, manufactures its own fuel, and harbors a shadow biosphere that has survived unchanged since the dawn of time. As we continue to drill deeper into the ancient cratons of South Africa, the shield rocks of Canada, and the seabeds of the Pacific, we are not just exploring Earth's history, we are exploring the fundamental limits of life itself. The discovery of Earth's ancient water systems suggests that the universe may be far wetter, and perhaps far more alive, than the dry surface of our neighbors would lead us to believe.